ready to master programming in C from scratch. In this complete beginner's tutorial, I'll teach you everything you need to know, from writing your first program to understanding compilers, IDEs, and debugging like a pro. Whether you're a student or just starting your coding journey, this is the perfect place to begin. Let's dive in. Getting started with C programming, a gentle introduction by the programming professor. Before we dive in, let's take a quick look at the roadmap for this module. We'll begin by discussing what programming is and why it's so essential, not just for software developers, but for problem solving in general. Then we'll look at the structure of a basic C program and walk through its components step by step. After that, we'll explore how to interact with users using input and output, and how to write clean, readable code with comments and whitespace. We'll also cover how to handle common programming errors, both syntax errors that prevent your code from compiling and logic errors that produce incorrect results even when your code runs. Then we'll zoom out and explore what's happening behind the scenes when your program runs, how the processor, memory, and storage work together. We'll also introduce you to tools like compilers and IDEs, which make programming easier and more efficient. Finally, we'll wrap up with a bit of history about the C language and summarize everything you've learned. Let's begin by answering a fundamental question. What is a computer program? Simply put, a program is a set of instructions that a computer executes one at a time. These instructions fall into three main categories: input, process, and output. Input refers to how a program receives data, for example, from a keyboard, file, or sensor. Processing is where the program performs calculations or logic, like adding two numbers or comparing values. Output is the result of that processing, displayed on the screen, written to a file, or sent elsewhere. Programs use variables like x, y, and z to store and work with data. The value of a variable can change while the program runs, which is why it's called a variable. At the core, every program is just a chain of these basic operations: get input, do something with it, and then output the result. To make this idea even more relatable, think of a program like a recipe. When you cook something, you follow a list of instructions. Mix 1 stick of butter with 1 cup of sugar. Add an egg. Bake for 8 minutes. Each instruction has to happen in a specific order, and if you skip a step or do something wrong, like adding the chocolate chips after baking, it won't come out right. Programming works the same way. You give the computer a series of steps, and it follows them exactly. It doesn't guess your intentions or fill in missing steps. It only does what you tell it to do. So learning to program means learning to think clearly, break problems into steps, and write those steps in a way the computer can understand. Before we write actual code, let's think about what it means for a computer to execute instructions. Unlike humans, computers don't infer meaning or skip steps. They follow instructions literally and in the exact order you give them. This first programming activity introduces that idea by letting you rearrange a small set of instructions and run them to see what happens. It focuses on how a variable, called m, changes value step by step. You can assign a value, modify it with math operations, and print it. By experimenting with different orders, you'll quickly see how just changing the sequence of these simple instructions leads to very different results. The goal here isn't to memorize syntax, it's to start developing your logic skills. Understanding this kind of step-by-step thinking is the key to writing correct, predictable programs, no matter what language you use. Let's look at a specific example of what this kind of instruction sequence looks like in code. In the program shown, we declare a variable m, assign it a value, modify that value by multiplying or adding to it, and then print the result using printf. By changing the order of these lines, even slightly, you'll get different outputs. For instance, if you print m before you double it, the printed value will reflect its original value, not the updated one. This reinforces the core concept that computers execute instructions line by line, in the exact order they're written. There's no guessing or backtracking. This also gives you your first taste of working with variables, using arithmetic operations and displaying output, all essential parts of programming in C. It's a small program, but it captures how structure and sequence control behavior in code. Programming isn't just about learning syntax, it's about developing a way of thinking. In the industrial age, mathematical thinking was essential. But in today's information age, computational thinking is just as important. Computational thinking means solving problems by designing step-by-step instructions, also known as algorithms. It's the thought process behind programming, and its value goes far beyond just writing code. For example, if you can break down a problem like calculating a triangle's area or averaging a list of numbers into a sequence of steps, you're already thinking like a programmer. The skills you build while learning to code, like analyzing a problem, identifying patterns, and creating repeatable processes, apply to any field, from science to business to education. Computational thinking is a mindset that helps you understand not just how to tell a computer what to do, but how to think logically and methodically about any challenge. Let's now look at a very simple C program and see how it works. Every C program starts execution in a function called main, and everything between the curly braces is part of the program's logic. Inside this function, we typically write one statement per line, each ending with a semicolon, much like sentences end with a period. In the example shown, we declare an integer variable called wage and assign it a value of 20. Then, using the printf function, we output the phrase salary is, and then the result of multiplying wage by 40 hours per week and 52 weeks per year to calculate an annual salary. Finally, the return 0 statement tells the operating system that the program ran successfully. This simple program shows how to declare variables, assign values, perform calculations, and print results, all fundamental operations in C. Moving on, let's take a closer look at how we get input from a user in C. Input allows us to write programs that aren't static. They can change behavior based on user-provided values. In C, we use the scanf function to read data from the keyboard and store it in a variable. For example, scanf %d, ~wage reads an integer and stores it in the variable wage. The ampersand symbol is used to specify the memory address where the value should be stored, a concept you'll explore more when learning about pointers. In the example, after getting the user's wage, we calculate the annual salary by multiplying it by 40 and 52, then print the result using printf. This introduces the idea of interactive programs, ones that respond to user input and perform calculations based on it. Understanding how input and output work together is key to building useful programs. Now let's talk about how text is printed in C. The printf function is used to display output on the screen, and it prints exactly what you give it. If you print 3 strings one after another using separate printf statements, they will all appear on the same line unless you manually insert line breaks. To start a new line in the output, you include the newline character \n inside the string. For example, printf hello \n prints hello and then moves the cursor to the next line. This level of control over formatting is important because the way output is presented can affect how easy it is to read or understand. By experimenting with different combinations of printf statements and newline characters, you can learn how to structure your output clearly and consistently, an essential skill as your programs become more complex. In addition to printing plain text, we often want to output the value of variables. This is done using printf with format specifiers. For integers, we use %d, which tells printf to substitute that placeholder with the value of a given variable. For example, printf %d wage will display the number stored in the variable wage. If you want to print a label along with the value, you can combine a multiple printf statements. In the example on the slide, wage is printed first, followed by the value of wage, and finally a new line. This formatting technique is widely used in all kinds of programs to show results, debug values, or communicate with users. Learning how to format output cleanly makes your programs much more useful. You can also make your output more concise and readable by combining multiple items into a single printf statement. Instead of printing text and variables with separate calls to printf, you can include both in one line using format specifiers. For example, printf wage is %d\n wage prints both the label and the value of wage in a single, clean output. This not only saves code, but also makes your output structure easier to understand. Programmers often use one output statement per logical line of output, aligning their code with what they want the user to see. As shown on the slide, the final result looks neater, and the code reflects the output layout more clearly. Combining output this way is a good practice to adopt early on, especially as your programs begin producing more complex results. Clean, intentional formatting improves readability for both the user and the programmer. Let's now talk about how we include comments in our code and why they matter. Comments are notes you add to your program for humans to read. They're completely ignored by the compiler, so they don't affect how your code runs. In C, there are two types of comments: single-line comments that start with // and multi-line or block comments that begin with /* and end with */. Single-line comments are great for quick notes next to a line of code, while block comments are better for longer explanations or documentation. Comments are essential for making your code understandable, both to others and to your future self. They explain what the code is doing and why, which is especially helpful when you return to a program weeks or months later. Learning to write clear, meaningful comments is a habit that will serve you throughout your programming career. Alongside comments, whitespace also plays an important role in writing readable code. Whitespace includes spaces, tabs, and blank lines. While the compiler mostly ignores it, humans rely on it to quickly understand the structure of a program. Good use of whitespace separates different parts of your code visually, making it easier to scan and debug. For example, blank lines can divide logical sections, and indentation helps clarify the structure of blocks like loops or conditionals. It's also helpful to align operators and variable declarations, and to put spaces around operators like equals, plus, and asterisk. These small stylistic choices make your code much more approachable, especially in team settings. While there's no single correct style, being consistent and intentional with your formatting is what matters most. Clean, well-formatted code not only looks professional, but also reduces the chance of making errors during development. To show just how important whitespace can be, let's compare two versions of a simple program, one written with clean formatting and another with poor formatting. In the well-formatted version, the code is clearly separated into blocks with consistent indentation. It's easy to see where variables are declared, where calculations happen, and what's being printed. In the poorly formatted version, everything is jammed together. There are no line breaks, no indentation, and everything looks chaotic. While both versions may compile and run the same way, only one is pleasant to read and maintain. This example makes the case for writing code not just for the computer, but also for yourself and anyone else who might read it. Good formatting is a sign of a thoughtful programmer. It communicates intent and structure, even before someone reads the comments or gets into the logic. Now that we've looked at how code is written and formatted, let's see how it's compiled. When you write code, you're using a high-level language that humans can understand. But computers only understand binary, sequences of zeros and ones. A compiler translates your code into machine language so the computer can run it. This process happens from left to right, line by line. The compiler looks for statements, generates machine code, and ignores things like whitespace and comments. This is why even poorly formatted code can still run, as long as the syntax is correct. However, the compiler is very strict about syntax. It won't let even small mistakes like a missing semicolon go unnoticed. Understanding how a compiler processes code gives you insight into why some errors are reported the way they are, and helps you debug your programs more effectively. That brings us to a common challenge: syntax errors. These occur when you break the rules of the programming language, such as forgetting a semicolon or a closing parenthesis. Syntax errors prevent your program from compiling, and the compiler will display an error message to tell you something's wrong. In the example on the slide, the programmer forgot the semicolon after the first printf statement. The compiler points out where it expected the semicolon and shows exactly where the issue occurred. This is a typical example of a syntax error: small, easy to make, and sometimes hard to spot. Fortunately, the compiler helps by flagging the problematic line. Learning to read and understand compiler messages is an important skill, especially early on. Once you fix the error and recompile, your program can run correctly. As a beginner, you'll encounter syntax errors often. It's all part of the learning process. While compiler messages are helpful, they aren't always perfect. Sometimes the error message you see isn't actually describing the root problem. It's just the compiler's best guess. In the example on this slide, the code is missing parentheses around the string in a printf statement, but the compiler mistakenly reports that a semicolon is missing. This happens because the compiler expects certain patterns, and when it encounters something unexpected, it may get confused. Often, the error isn't even on the line the compiler highlights. It might be a few lines earlier. That's why it's important to look around the reported location and not just focus on that single line. Over time, you'll get better at spotting the real issue quickly. Learning to interpret compiler errors is part art, part science, and it gets easier with experience. A useful strategy for dealing with compiler errors is to focus on the first one. When your program has a mistake, the compiler might produce a long list of errors. But in many cases, most of those errors are just side effects of the very first mistake. For example, missing a semicolon early in your code might confuse the compiler so much that it reports errors in the next 10 lines. Don't let that overwhelm you. Start by fixing the first error, then recompile. Often, many of the later errors will vanish. This first error first strategy is especially useful when you're just starting out. It helps you stay focused, keeps you from chasing your tail, and makes the debugging process far less frustrating. Remember, compile frequently, fix one error at a time, and build your code up gradually. So far, we've looked at syntax errors that prevent code from compiling, but now let's talk about logic errors, mistakes that happen even when your code compiles perfectly. A logic error means your program runs, but it doesn't do what you intended. These bugs can be tricky because there are no red flags from the compiler. For instance, you might accidentally add two variables when you meant to multiply them. The program runs and prints a result, but the result is wrong. In the example shown, the programmer intended to calculate the total number of beans by multiplying num beans by num jars, but accidentally used a plus sign instead. This kind of mistake is easy to overlook. Finding and fixing logic errors requires you to think through what the code is doing line by line, compare it against what you meant to do, and often test your code with different inputs to catch incorrect behavior. One way to reduce these kinds of errors is to compile your code frequently. A common beginner mistake is to write dozens of lines of code before testing anything. Then when errors appear, you don't know where to start. Instead, it's much better to compile after every few lines. Write a small piece of your program, compile it, and fix any errors before moving on. This helps you identify exactly where things go wrong and makes debugging much easier. It also builds your confidence, because you know that each piece of your program is working before adding the next. Even experienced programmers use this incremental approach. Programming is a process of building and refining, just like writing an essay or building something with Lego. So don't try to finish the whole program at once. Compile often, test as you go, and you'll make faster progress with fewer mistakes. Even when your code compiles, the compiler may still issue warnings. Warnings are messages that something might be wrong, even if the compiler is still able to produce an executable file. Think of warnings as yellow lights. They don't stop you, but they tell you to proceed with caution. For example, if your code tries to divide by 0, some compilers will give a warning. The program might compile, but if you run it, it could crash or produce incorrect results. Good programming practice is to always fix warnings, not ignore them. Many programmers even configure their compilers to show more warnings using flags like wall in GCC, which helps catch subtle bugs early. Treat warnings as a favor from your compiler. It's trying to help you catch problems before they become real bugs. Writing warning-free code leads to more robust, maintainable programs. Now let's take a closer look at how computers actually work under the hood. Understanding how a computer executes programs can help you become a better programmer. Just like it helps a car owner to know what's going on under the hood, programmers benefit from knowing what's happening behind the screen. At the most basic level, computers work using switches, electrical devices that control whether electricity flows. In the 1800s, switches were mechanical and manually operated. But in the early 1900s, engineers developed electronic switches that could be controlled automatically. If a positive voltage was applied, the switch would turn on, representing a 1. If there was no voltage, it was off, representing a 0. These ones and zeros are called bits, short for binary digits. By combining lots of switches into circuits, engineers were able to build machines that could perform calculations, such as adding or multiplying numbers. These circuits became increasingly complex over time, leading to the development of the first electronic computers in the 1930s and 1940s. These early computers contained thousands of electronic switches and filled entire rooms. Even so, they could already perform thousands of calculations per second, an incredible feat for the time. As technology advanced, engineers created components called processors to handle lists of instructions. At first, processors were enormous and configured manually using switches. But today, processors are incredibly compact, often no larger than a postage stamp, and contain millions or even billions of switches. These processors are designed to execute instructions rapidly, using internal circuits to fetch, decode, and perform each operation. This evolution in hardware made computers faster, smaller, and more accessible, paving the way for the modern devices we use every day. To understand how programs run, we also need to understand memory. In a computer, memory stores both instructions and data using binary, zeros and ones. Think of memory as a long row of mailboxes, each with a numbered address. You can store a value in a mailbox and retrieve it later using that address. For example, mailbox 0 might contain an instruction, mailbox 97 might hold a Celsius temperature, and mailbox 99 might be where the converted Fahrenheit temperature is stored. The processor executes instructions by reading them from memory, performing operations, and storing results back into memory. Everything happens using bits, on or off signals, stored and manipulated at lightning speed. This mailbox analogy is a helpful way to visualize how memory works. It's not just a place to store numbers. It's where the processor lives, breathes, and carries out the logic of your programs. Let's take a moment to understand how a computer actually works at a fundamental level. At its core, a computer is just a processor interacting with memory. The processor's job is to read instructions from memory, execute them one at a time, and, if needed, store the results back into memory. For example, imagine a program that calculates an annual salary based on an hourly wage. The instruction might look like wage equals 20, followed by a calculation like wage multiplied by 40 multiplied by 52, which results in 41,600. That result is then output to the screen. This simple example captures the entire cycle. Fetch an instruction from memory, perform a computation, and deliver the result. Every program you write, no matter how complex, eventually boils down to this cycle of instruction and execution. Understanding this interaction gives you insight into how your code becomes action. Now let's talk about what those instructions look like. At the lowest level, processors understand simple commands like add, multiply, or jump. These instructions follow a predictable format. Each instruction corresponds to a specific operation in the processor. There are commands to add, subtract, multiply, divide, and jump to another instruction in memory. For example, mul97, 9, 98 means multiply the value in memory location 97 by 9 and store the result in location 98. These instructions are usually represented in binary, like a series of zeros and ones. But for readability, we often use simplified symbolic representations called assembly language. These low-level operations are the building blocks of all software. Whether you're playing a video game or writing a text document, at the hardware level, your computer is just executing thousands or millions of these instructions per second. The sequence of instructions a programmer writes, whether in C, Python, or assembly, is what we call a program. When you power on a computer, the processor immediately starts reading instructions from memory, beginning at location 0. It processes them one by one, instruction 0, then 1, then 2, and so on. If a jump instruction is encountered, the processor changes its path and jumps to a new instruction elsewhere in memory. This is how loops and conditionals work. In a basic example like converting Celsius to Fahrenheit, a programmer might store the input temperature in memory location 97, execute a series of instructions to compute the Fahrenheit value, and then store that result in memory location 99. If those locations are connected to switches and lights, like in old systems such as the ENIAC, the input can be set physically and the result viewed immediately. It's a clear demonstration that programs are just step-by-step instructions, executed by hardware. Back in the 1940s, writing those instructions meant literally working with zeros and ones, machine code. For example, you might have had to write long sequences of ones and zeros, which would tell the machine to perform a multiplication. But writing in binary is extremely tedious and error-prone, so programmers developed assembly language, a human-readable set of codes like mul97, 9, 98, that gets translated into machine code by a program called an assembler. This made programming more approachable, but it was still low-level and tightly tied to the hardware. In the 1960s and 70s, high-level languages like Fortran and Algol were developed to express algorithms and formulas more naturally. Instead of thinking about registers and memory locations, programmers could write expressions like f equals 9 divided by 5 times c plus 32. These high-level programs are then translated into executable machine code by a compiler. This progression, from binary to assembly to high-level code, was a major leap in productivity. To make programming even more convenient, developers use tools called IDEs, integrated development environments. Writing software involves several steps: editing code, compiling it, testing it, and debugging it. While each of these tasks can be done with separate tools, IDEs combine them into one place. A modern IDE includes a text editor for writing code, a compiler to translate the code, and a debugger to find and fix errors. Most IDEs also have features like file management, a project navigator, and a built-in console for running programs. This all-in-one setup saves time and reduces complexity, especially for beginners. Some popular IDEs for C programming include Visual Studio Code, CLion, and Xcode. Some IDEs are installed directly on your computer, while others are cloud-based and accessible through a browser. Whether local or online, IDEs are now standard tools in the software industry, and learning to use one early on will boost your development efficiency. Even though IDEs combine many tools, it's helpful to understand what those tools actually do. One of the most useful features is syntax highlighting, where different elements of your code, like keywords, variables, and strings, are displayed in different colors. This makes your code easier to read and helps you spot common mistakes, like missing quotes or unclosed parentheses. IDEs also typically include automatic indentation, which ensures your code stays neatly formatted, and delimiter completion, which adds closing brackets or parentheses for you. All of these features work together to make programming faster, less error-prone, and more manageable. Another key feature of many IDEs is the built-in console and command line interface, or CLI. The console is a text-based window where your program runs. It's where you'll see output and where you can type input when your program asks for it. The command line interface allows you to run programs by typing commands directly, which can be faster and more flexible than using buttons or menus. One major benefit of the CLI is that it lets you pass command line arguments to your program. For example, a command like ls-a tells the system to run the ls program and include hidden files in the output using the flag -a. In your own programs, you can make use of arguments passed this way to customize behavior without changing your code. The CLI is a powerful tool, and learning to use it alongside your IDE will make you a more capable and efficient developer. The word computer has gone through a major transformation over time. Originally, it referred to a person who performed calculations by hand, someone you might hire like an accountant. In the 1940s and 50s, the term shifted to describe massive machines that filled entire rooms. These machines were shared by multiple users and primarily used by governments, universities, and large corporations. By the 1970s and 80s, the concept of the personal computer, or PC, took hold. These were smaller systems for home or office use that no longer had to be shared. Fast forward to the 2000s and 2010s, and computer refers not only to desktops and laptops, but also to smartphones, tablets, smart TVs, and even embedded devices inside cars, appliances, and medical equipment. As hardware matured and became more stable, people began distinguishing between the physical computer, called hardware, and the instructions it runs, known as software. Let's now explore what's actually inside a computer. A modern computer is made up of several key components. First, there are input and output devices, things like screens, keyboards, mice, microphones, and speakers. These are how users interact with the machine. Storage is another major part. Most modern computers use solid-state drives, or SSDs, which store files, programs, and other data. Unlike older hard drives that relied on spinning disks, SSDs use flash memory and are faster and more energy efficient. Then there's memory, specifically RAM or random access memory. RAM holds data temporarily while programs are running and is much faster than SSDs, though it loses its contents when the computer powers off. Finally, you have the processor or CPU, which runs all of the programs by executing instructions stored in memory. To keep everything running smoothly, the CPU also includes a clock that governs the speed of instruction execution, ranging from millions to billions of ticks per second. Another major innovation that shaped modern computing was the invention of the transistor. Early computers were large because they used vacuum tubes, but the invention of the transistor in the mid-20th century allowed engineers to build smaller, faster, and more reliable machines. In 1958, multiple transistors were placed on a single chip, called an integrated circuit, or IC. As engineers continued to shrink transistors, they discovered that they could double the number of components on a chip roughly every 2 years. This trend became known as Moore's Law. Although the timing hasn't always been exact, the general principle has held true for decades and has driven massive leaps in computing power. By 1971, Intel released the first single-chip processor, the Intel 4004, which had 2,300 transistors. Just a few decades later, chips contained billions of transistors and supported multiple processing cores. This exponential growth has powered everything from laptops to smartphones to the cloud. One practical takeaway from Moore's Law is that adding memory, especially RAM, is a simple and cost-effective way to speed up your computer. Over time, as programs grow and multitasking becomes more common, your system may run into limits, especially if it doesn't have enough RAM to hold all active data and instructions. When that happens, the processor has to constantly shuttle data back and forth between memory and storage, which slows everything down. Think of it like a chef working in a kitchen. If their counter space is too small, they have to keep running back and forth to the pantry. But if you give them a bigger counter, they can keep more ingredients close by and work more efficiently. Similarly, adding more RAM means the processor has more immediate access to what it needs. Because memory prices drop over time, upgrading RAM in an older computer can deliver a noticeable performance boost for relatively little cost. Let's now take a brief look at the history of the C programming language itself. In 1978, Brian Kernighan and Dennis Ritchie, working at AT&T Bell Labs, published a book about a new language they developed called C. It was based on a previous language named B, which itself came from BCPL. C was simple, powerful, and fast, and it quickly became the dominant language in the 1980s and 90s. Then, in 1985, Bjarne Stroustrup extended C to create C++, which introduced object-oriented programming along with other features. The ++ in the name comes from the increment operator in C, suggesting that C++ is one step beyond C. Despite the arrival of newer languages like Python and JavaScript, C and C++ remain widely used today, especially in systems programming, embedded software, and performance-critical applications. In fact, according to the TIOB index from 2023, C ranks second in popularity, just behind Python, highlighting its ongoing relevance in the software industry. Programming is not just about writing code, it's about solving problems. Just like a chef might know English, but still needs creativity and structure to write a good recipe, knowing a programming language doesn't automatically mean you can write a great program. Programming is really about problem solving. You need to think methodically, break down a task into steps, and build a logical solution. One fun example of this comes from a real-world scenario: someone frustrated by mismatched socks. A friend proposed pulling out one sock at a time without putting them back, If there are only 3 types of socks, then by the 4th sock, you're guaranteed a match. That's an algorithm, a step-by-step solution to a problem. It's not about fancy code, it's about thinking clearly and strategically. That mindset is what separates someone who knows syntax from someone who knows how to solve problems with code. So why learn programming? One of the biggest reasons is the opportunity it creates in today's job market. Computing careers are relatively new compared to traditional fields like law, medicine, or engineering, but they're already some of the most in-demand and best-paid jobs out there. Roles like software developer, cybersecurity analyst, data scientist, and systems engineer often rank at the top of job satisfaction lists. These careers offer great salaries, flexible working environments, and strong long-term security. Even if you're not planning to become a full-time developer, understanding programming can be a major asset. Most computing roles require at least some exposure to code, and that knowledge opens doors. In a 2022 ranking, Information Security Analyst ranked 1, and Software Developer came in at 5, both examples of how central computing skills have become across industries. But it's not just for computing careers. Programming can also be a game changer in fields like chemistry, business, engineering, marketing, and more. For example, Kelly, a chemist, started writing small programs to improve her analysis of clinical trials, and now her coworkers rely on her for custom tools. Paul, a civil engineer, used programming to automate repetitive documentation tasks, saving his team time and frustration. Ethan, a business major, picked up SQL and started automating sales reports. Now his responsibilities have expanded beyond his original role. And Eva, who majored in environmental science, used her coding skills to make her company's website interactive, all based on what she voluntarily learned in college. These stories show that programming isn't just for software engineers. It's a powerful tool for anyone who wants to automate, optimize, or innovate in their work. One of the most valuable benefits of learning programming is how it sharpens your thinking. Writing correct code requires you to be precise, logical, and methodical. This type of thinking, often called computational thinking, can improve your ability to write, speak, and solve problems in all areas of life. New programmers sometimes feel frustrated because the computer seems so unforgiving. One missed semicolon and the whole program crashes. But this need for precision is part of what makes programming such a powerful mental discipline. It trains you to be clear, to plan ahead, and to spot small mistakes. And those skills don't just help with code. They carry over into writing reports, organizing projects, or even solving personal tasks more efficiently. Programming teaches you how to think more clearly and critically, and that's a skill worth developing, no matter what career path you take. That said, learning to program is not easy. In fact, it's probably very different from anything you've done before. Many students struggle at first, and that's okay. Think of it like learning to walk or play an instrument. You'll stumble, make mistakes, and feel confused sometimes. That doesn't mean you're bad at it. It just means you're learning. Programming is a blend of knowledge and skill. You can't just read about it, you have to practice it. You need to write expressions, build loops, make mistakes, and fix them. And yes, it takes mental energy. There's no checklist that works for every problem. Programming requires real thinking. But stick with it because the payoff is huge. You're learning a skill that can change your career, expand your thinking, and open up new opportunities. And every bug you fix is a step forward, even if it doesn't feel like it at the time. Let's talk about something that catches many beginners off guard: white space and formatting. When you're working on programming exercises, especially those checked by an auto-grader, your output has to match the expected output exactly. That includes spaces, tabs, and line breaks. Students often say, my program is correct, but it's failing because of whitespace. And yes, that's frustrating at first. But it's also a valuable lesson. Programming requires attention to detail, something that becomes more and more important as your projects grow. If your output is supposed to end with a new line, it must end with a new line. If there's an extra space, that's a problem. So whitespace isn't just cosmetic, it's part of writing precise, correct programs. And learning to be that precise, even in small things, helps you become a stronger programmer overall. It trains you to think critically and spot the kind of issues that cause bugs later. That leads us into one of the core truths about programming. It's all about precision. Computers don't assume anything. They do exactly what you tell them to do. So if you use equals when you meant equals equals, or accidentally use I instead of J, the computer won't guess your intent. Even subtle issues, like using divided by 2 instead of divided by 2.0, or counting from 0 to 9 instead of 0 to 10, can change your program's behavior completely. This kind of precision isn't always expected in other subjects, where partial credit might be given for having the right idea. But in programming, close enough often isn't good enough. That's why even whitespace matters. Developing this precision-focused mindset will not only help you debug more effectively, but also write cleaner, more robust code from the start. Programming teaches you to pay attention to the details, and that's a valuable skill far beyond just writing code. To wrap up this module, let's review what we've covered. We started with the basics of what programming is and how C programs are structured. We looked at how to write your first C program, how to read user input with scanf, and how to print output using printf. We explored how comments and whitespace make your code readable, and how to identify and fix both syntax and logic errors. We went under the hood to understand how processors, memory, and storage work together to run your programs. Then we looked at programming tools like compilers, IDEs, and the command line interface. We touched on the history of the C language and its ongoing importance in the industry. Finally, we discussed how programming develops your precision, logic, and problem-solving skills, making it valuable not just in tech jobs, but across every field. Learning C is just the beginning, but it's a strong foundation that sets you up for success. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.